Hey there, Physics 30. Welcome to Unit 3 EMR. We are going to get into electromagnetic radiation. This is probably the most important unit in Physics 30. It deals with a lot of things that how our world works. Okay, like the electric unit and the electric chapter and magnetic chapter. They're both good. We can kind of see them. We can play with electricity. We can electrocute map by accident, all those things. Okay, but when we get into Unit 3 here, we're actually going to bring them together and talk about cool things like photons and gamma rays and how these things all work and how we found the speed of light. So yeah, this first lesson, there's not a lot going on. All right. So for this chapter, we're going to do, for chapter 13, it's a really long chapter. I'm sure you guys might have noticed. We're going to basically do everything up to polarization. All right, and kind of in one go here. There's a little bit here and there of mirrors and lenses and dispersion. There's some math, but again, it's a little more theory and bringing some stuff together. Especially these first two lessons. There's quite a bit of theory in here, so kind of bear with me. You're gonna have to listen to me talk for quite a bit. All right, so Unit 3 deals with EMR and the battling theories of what light was composed of. All right, so Newton here, he says particles because the energy from the sun, the energy from the sun gets to the earth. This is the earth. Very nice earth. All right. And since the energy from the sun is getting to the earth, it has to be a particle because, all right, it has to be a particle because there's no medium. All right. There's no medium, so how on earth does it do that? Okay, so that was basically, that was Newton and most of the people who followed him for quite a while. And then Higgins comes along, and Higgins is like, listen, it's obviously waves because we have interference patterns, right? If I send a light ray like this and a light ray like this, we can get a light ray like this, right? We get interference patterns, so it's obviously a wave. But then Newton's like, man. So, of course, then comes along Einstein, and he's just like, you guys are both really smart. I agree with both of you. It's actually both. All right, so we're going to get into this idea how something can both be a particle and a wave, but not both, but not really neither. And kind of depending on what we do, it just is like, bam, changes things up. Okay, we're going to be dealing basically a little bit with the units we've done, but we're going to spend a little bit more time in this, okay, in waves. We're going to talk a little bit more about waves in here and kind of all that kind of stuff. Those equations are what's going to see the most in here. All right, you also know, remember the back of your formula sheet. We're going to see those lots too. Okay, come on, next page. There we go. The back of our formula sheet, right, we've basically covered everything in here, I think, except for Planck's constant and the atomic mass. So we've done everything. I guess this is more correct. There's until speed of light here. All right. Yeah, you guys should know all those. The index of refraction, that'll be in this unit. All right, Planck's constant will be in chapter, I believe it's in chapter 14, not 13. Atomic mass units in the last three chapters. Okay, remember to always check your prefixes. Okay, we're going to be using those a lot because we're talking about very, very small or very, very large objects right now. And you guys should know your charges, your stuff like that. Okay, so this is still where we're going to be. We don't get into this here. All right, this fermions, we don't get into this for quite a while, so don't worry too much about this for now, but it's kind of interesting once we get there. All right, so you can do your anticipation guide and then read section 13.1, which I'm reading, answer the questions on separate sheet of paper. Make sure you type those out, right? We're typing now so that you can submit those to me, all right? Vocab, a little bit of vocab in there as well. All right, so James Maxwell in the 1860s, he basically said, well, electromagnetic theory linked the concept of electricity magnetism and predicted that even without wires, changing electric fields would produce a changing magnetic field and vice versa. And so what he came with this idea was electromagnetic waves, right? And it's complex, but it looks like this, okay? It looks like this, all right? If we have an electric field, and we increase it, then decrease it. We're going to also create a magnetic field, increase it and decrease it. Now we get an electric field whenever a oscillating charge. So charge is oscillating. So basically we have a negative that's going up and then down, up and then down, right? And so we're going to get an electric field that gets smaller, then larger, then smaller, then larger, then smaller, larger. So that gives you that. Now, perpendicularly, we're going to get a magnetic field that also does this. So it was confusing because we have a charge creating a wave, right? But not only is it's one charge, not only creating one wave, it's creating two waves. And so what we actually have is we have two waves moving in a direction that are representing an oscillating charge. This was known as electromagnetic waves, okay? All right, and these are electromagnetic waves, and we're gonna call it EMR. EMR is short for electromagnetic radiation. All right, and they can be observed directly from the source or indirectly through reflection. Okay, that's an important thing, is that these things reflect. They don't reflect like particles. They reflect a little bit more properly. All right, you can see what I'm talking about if you click on this link and just enable your flash. Just click on the thing and it'll actually open up. You can actually see what it means is you have a moving oscillating charge. It's going to create a field, and that's going to move across. So the charge, in theory, right, it's hard to tell, is there's a charge that's doing this motion up, down, but it's actually moving this way. So the charge is kind of moving up and down, but it's moving in this direction, but it's actually a particle that's doing that. And the waves kind of oscillate to each other, all right? When the particle's at rest, it generates an electric field, right? But then when it's moving, it generates a magnetic field. And so we have a charged particle that's constantly accelerating. So it's going from rest to moving, from rest to moving. And so when it does that, it's going to cause the magnetic field to go from 0 to max to 0 to max. Okay, it's weird. I'm still teaching with my hands, even though you guys can't see it. So the electric and magnetic field, they're perpendicular to each other, and they travel in a direction perpendicular to the direction of the accelerated charge. So everything's kind of perpendicular, and we're going to travel in a direction. So this is the main theory as to how light itself works. All right. Okay. So you can kind of picture this, but basically explain how accelerating charges produce electromagnetic radiation. Look at the case where positive charge and negative charge are oscillating towards and away from each other. So what this can kind of look like is that we have a positive charge and a negative charge, and they're going to go towards each other, but then actually not hit. They're going to pass each other. All right, so they're just off. They're going to pass each other, and once they do pass each other, then they'll pull each other back. They're basically going to oscillate back and forth. All right, I tried to use this. It doesn't work. Okay, but basically when you do that, you get this magnetic, electric, magnetic, electric, magnetic, electric interference back and forth, okay? When the charges stop moving, there's no magnetic field, therefore no EMR. So the charges are actually always kind of moving in a way. All right, so when the charges move away from each other, they generate a magnetic field as well as an electric field. Okay, however, the magnetic field generated is not constant as the current in the region is changing. From Faraday, the changing magnetic field generate an electric field. This gives us a changing magnetic and electric fields. So we have both changing and electric and magnetic. All right, so Maxwell was kind of the one that first really predicted all this stuff. And he never produced or detected non-visible light waves. So basically saying is that this could happen, these rays and these waves could happen at different frequencies and different speeds and all that kind of stuff. And unfortunately, Maxwell never produced and detected a non-visible wave. He only predicted their existence. In 1886, Heinrich Hertz was able to do so. Hertz, that name sounds familiar, right? Hertz. Okay, and he's the guy that came up with friction. So he basically detected them with a wave, right? And he basically said, okay, well, what if I have something that's in a frequency of times 10 to the 9? Okay, and he detected them with an antenna, and the receiver was turned to the same frequency as a radiator, and he induced current flow in the radiator. So he was actually causing a current to go through something, and it radiated something that he could pick up across the room. He showed that EM waves move at 3 times 10 to the 8 meters per second, using the formula V equals F lambda, which we've done, and have the properties of light waves. He showed reflection, refraction, diffraction, interference, and polarization. So he called these waves radio waves. All right, he called them radio waves. And so now he actually basically not discovered radio, but he discovered radio waves and postulated what they were, but he invented the idea, the technology that leads us to leads us to essentially what is a radio tower, right? And how radio works today. Radio still works in the same concept. You use a current, an oscillating current, going up a tower, and that creates a voltage, and then it creates an electric field, which creates a magnetic field, which then we can send out waves in all directions, right? So basically, your car can pick that wave up at some point. All right. So this is kind of what his setup looked like. 10 to the 9 hertz, right, means that hertz is how many times per second. So 10 to the 9 times per second, right, which is really, really high. Detecting them with an antenna. So since he had really high frequency, he had he had a relatively low frequency compared to other things. He had long wavelengths. And so this is his setup, right? And so what he had here is he had basically a coil to produce a high voltage, and then it basically would be sparks. And so you'd have spark, and then it would create electromagnetic waves. These these waves would then be picked up by this antenna. So it's interesting that he was sending something through space being picked up, right? And so now this is the idea, okay, well now we're getting to this concept of how can stuff flow from one object to another that was originally created by a particle, but now is flowing without a medium, right? There was a medium here, but you didn't need it. There was no physical contact. All right, he also predicted the speed of light in a vacuum using our V equals F lambda. All right. So the antenna needs to be a good conductor because EMR will induce a current in it. And so what's kind of cool about this is you think about it, what you got is you got a radio tower at the top of the radio station. So you got a radio tower, kind of looks like this. All right, and they're going to basically have a current, a changing current. So they're going to send electrons up and down, move the electrons. And that's going to send out a radio wave to your car. Okay, so you got your car here. And then you got your car and you got an antenna. So when this radio wave hits your antenna, it's going to cause the electrons to move up and down. Okay, up and down. So electrons move up and down inside your car. There we go. Electrons move up and down inside your antenna, which is then attached to said speakers. Right, said speakers. When they move up and down, the speakers are then told basically to contract and expand based on the frequency and what they're hearing, right? So they contract and expand, which then contracts and expands the sound, the air in your vehicle, right? Which then you hear. Which then you hear. How do I draw near? Not bad, actually. All right. So which then you hear inside your vehicle. So this idea of how you can turn on the radio and you can hear something coming from so far away is pretty incredible technology, but it's also super old technology. Right, it's super old technology. It's been around since like the late 1800s, and now we just use it in vehicles, kind of for music and for fun. How your phone and stuff receives information is purely EMR. It doesn't really have to do with any kind of sound waves or anything like that, or as much moving electrons. So they discovered radio waves, but then people started researching. Well, if we know our light is one type of EMR. I know radio waves are EMR, but what we kind of figured out was that the light really fits in this kind of frequency box, right? Light fits here, and then radio waves kind of fit over here. Well, there's got to be stuff in between, right? There should be stuff in between. And then they started discovering, well, what if there's stuff even beyond, right? And so we get what's called the electromagnetic spectrum. So there are different types of electromagnetic radiation depending on the frequency, wavelength, and energy of the wave. Although these characteristics are different, the velocity of electromagnetic radiation is always the same. So energy, frequency, and wavelength can change. Okay? Energy, frequency, and wavelength can change, but the speed of the light is always the same. All right? Not going to be a little confusing because if they're moving at the same speed, should they have the same energy? The answer is not really no, because you're saying you're thinking kinetic energy. These things are weightless. They don't have a mass, right? I can't open a jar, shine light into it, and then close the jar, and then it's heavier. They don't have a mass, so they don't really have what's considered kinetic energy. They have a different type of energy. All right. So what we'd have here is we basically have the entire spectrum. All right. And we've got from low energy, okay, these are low energy, to high energy. Okay, high energy. And we're not talking about the energy being slightly more. We're talking about it being factors of 10 more, right? So every time I go up one of these, right, this is 100 times more energy. This step here is another 100 times more energy kind of idea. So you can imagine the difference between a gamma ray and a radiation wave, or radio wave. All right, I know you guys have done Bio 30 already, so you've probably seen some of this as it is, but I'm still going to go through it a lot, okay? So we have basically the different types. We have radio waves, microwaves, infrared, visible light, UV, X-rays, and gamma rays. All right, you'll notice that they all kind of overlap a little bit because it's the characteristics kind of blend in the middle. All right, visible light is basically the range of frequencies or the range of wavelengths. I guess wavelengths is probably better. From 700 nanometers to 400 nanometers. If you look at the back of your formula sheet, nano means times 10 to the negative 9. Sorry, I'm pretty sure. I'm going to double check that because my brain's not working again. Yeah, nano means times 10 to the negative 9 meters. All right. So it only fits in this one very special part of the spectrum, right? We have everything that can go from 3 times 10 to the 4 meters, which is huge, right? 3 times 10 to the 4 meters is 3,000 meters for one wave. Sorry, 30,000 meters for one wave, right? All the way down to less than 3 times 10 to the 12, negative 12, right? So right in the middle, just a little small area, is 700 nanometers to 400 nanometers. Those numbers should be memorized. You should know those, all right? So we're going to go through radio waves. These are big, right? We use radio waves to send communications, all right, around. Then we have microwaves. We can use microwaves to basically microwave objects. Infrared. Infrared's kind of a heat signature. It's infrared because it's on the red side of the spectrum. So infrared. And then we have the violet end of the spectrum is ultraviolet. These are high energy, okay? Once we get past kind of our thing, the ultraviolet rays, they do sort of interesting things. They can start passing through things, all right, without interfering because they're so small, right, that they can go actually in between particles of things, right? Particles are far apart. Then we get X-rays, which you actually use for X-rays, and then gamma rays. These are bad. We don't want to be exposed to gamma rays. Gamma rays are not good for you, okay? X-rays are not great for you. UV, we've all heard UV rays can give us cancer in the skin if we have too much in the sun, right? But these are all high energy waves, right? Okay, all right, with gamma rays being the highest. The higher the energy wave, the more chance it has that can cause issues within our own body because when it hits something, it hits it with a ton of energy. It kind of is a bit of a destroyer, especially gamma rays. Now, X-rays are relatively safe. UV you're exposed to every day and you're generally going to be just fine. But gamma rays, when we especially get into this end of the spectrum, we're talking about some pretty serious consequences if you're dealing with this all the time. All right, and we'll kind of get more into what that looks like in the next couple chapters as well. All right, so we're going to go ahead and talk about a lot of these things and just, I'm not going to waste too much time. You guys should be able to, read through most of this. Okay, so the electromagnetic spectrum forms all forms of EMR while comparing their frequencies, wavelengths, and energies. Okay, note the higher the frequency, the lower the wavelength, and vice versa. So if I increase frequency, the wavelength goes down. Okay, visible light only makes up a small portion of the spectrum, and I just talked about that. And EMR can be observed directly in the form of light or heat, or indirectly by its effect on materials. So we can't see gamma rays, but we can see when it hits something, what it does to it, kind of idea. So popular diploma exam question involves you to perform a bunch of calculations, then determine the type of wave that you found without having the spectrum give to you. Okay. What you tune to when you listen to the radio is the carrier signal. Okay, so we're first going to look at basically this idea that you should have a concept. Obviously, we're not going to have a diploma question. I'm not going to ask you guys this type of question. I'll probably be within the light region. I'll say, is this more red or purple, right? Are we red or purple? And you kind of have to know which end of that we are. You should also know if it's close to red, but it's not in the range, and then it's infrared, and have an idea of where they are. So we'll go through all of the different types of waves. Okay, so Radio waves are emitted by various electric circuits. For example, 60 hertz alternating current sends out radio waves with a wavelength of 5,000 kilometers. All right. Radio waves can be used to transmit information from radio and television stations, and this has the least amount of energy. All right. When you tune your radio, it's the different signals, which is basically different frequencies, kind of, and they're chosen by the government. The government says you can use this frequency or this frequency. All right. When we get to microwaves, basically we're going to have microwaves that can have an induced current from EMR, which creates an intense electric field that creates arcs. All right. This is more where we're going to basically heat up food, where the energy of this rotation transfers through the food. They're also using cell phones, radar guns, garage door openers, stuff like that. So anything you kind of like send a signal is usually going to be a microwave. All right. And these microwaves, a microwave oven, right, it heats up basically water molecules. Okay. If you put metal in there, the reason that the metal gets sparky is because basically the EMR creates a current, which creates static, which creates arc. Right? And we don't want that. Okay, then we get infrared. For infrared, we're going to talk about it's any molecules above any temperature. Okay, will radiate infrared radiation. So any molecules that are hot will do that, and also different temperature objects result in different infrared wavelengths emitted. And so we can use this to kind of detect brain tumors or spotting prey like snakes. They deal in the infrared. The term infra means the below. Okay, so it means below the red end of the light frequency. All right, for example, when Felix Baumgartner jumped out, I showed you guys this Fix 20, he had used infrared cameras to track the position just because he was moving so fast, the infrared was actually easier. All right, then we get to visible light. Okay, so visible light, you do need to know that it's from 700 nanometers to 400 nanometers. All right, by memorizing those two, you can always calculate the frequencies. Right, you can memorize the frequencies if you want, but you need to know those two. Visible light has the smallest range, but it is the only one that can be detected by the human eye. Red light has the longest wavelength, and that's kind of it. So remember, though, you guys, the reason that you see something red is because an object absorbs all the red light, and your eye is actually receiving everything else. Okay. Yeah. So the colors we see are basically what's not absorbed. All right. So you can go ahead and you can watch this video. It's really good. Right. We've got this red tomato here. Okay. You can see why it's red. Okay. This is a good video. This one's also really interesting. This one talks about like the idea of like, is this blue? Right? Well, we all see that as blue and green, right? Blue and green, but maybe just from children were we told that something is blue or something is green. And this kind of video explores it. I really like it. It's not real long. It's only about 3 minutes, 3-4 minutes. So then we can get into things like mantis shrimp, for example. So this is the human eyes, what we can detect. Okay, we're essentially red, blue, and green are all the colors we can detect. We can detect the absence of them or the presence of them, right? Then you look at something like the mantis shrimp. Okay, this is what they can detect. They can detect all of these things. All right, this is what their rods and cones do. So if we could see like they can, we could also see into the into the ultraviolet. Right, I didn't see this. See into the ultraviolet, right? And not only that, we could also see all of the stuff inside of our visible light spectrum much easier, right? So for example, this teal area, we don't see great, right? They have cones to actually detect that exact teal area, right? So there's kind of this idea, okay? Yeah, that's kind of the idea of visible light. All right. So then we get to ultraviolet. Okay, ultraviolet is 400 nanometers to 9 nanometers. Okay, the prefix ultra means above, so it's above violet light, right? Makes sense. Okay, ultraviolet light can kill microorganisms. It can cause what you tan or sunburn. It can form vitamin D, cause melanoma. It can do a lot of stuff. But what's important is that the ozone layer, right? The ozone layer, okay, it absorbs a lot of the UV light, so we're protected from most. If we didn't have the ozone layer at all, you could only go outside for like a couple minutes before you'd start to burn, and that would be even in like the winter, right? The sun would be pretty bad. Okay. Let me get X-rays. We use X-rays basically for um, basically sending things and measuring, looking at bones, right? They used to use X-rays for basically telling, measure your foot size. You stick your foot in this little machine here, and you can measure your foot size based on that. They basically stopped using them, okay, in the 1980s because they realized that it's not good, okay. So they're high energy waves that can be generated by the rapid deceleration of high velocity electrons. So basically, when you get an X-ray machine, you have it creates high velocity electrons, and then it slows them down very quickly. And when it slows them down very quickly, it's going to give us this X-ray. Okay. They can go through soft tissue. They're blocked by minerals and bones. So they can go through the soft tissue, which is nice because we can see through the skin. We can see if something's broken. All right. And the last one we get into is gamma rays. Okay, so gamma rays, they're the highest energy. Okay, they're basically emitted during radioactive decay of unstable nuclei, and they're also released by pulsars. Okay, pulsars, neutron stars, and explosions of supernova. Okay, or novae. We're talking about huge, huge, huge events in space. All right, they give off gamma rays. I'm also talking about radioactive decay. This is basically why Chernobyl was bad. All right. So this explosion of supernovae, we're talking about basically a star decaying, an entire star decaying and then blowing up, right? Like there's so much energy and all this stuff, and so it's going to give off these bursts. All right. So the 1960s gamma ray bursts were first detected, ranging from fractions of a second to minutes long. All right. A gamma burst can emit more energy in 10 seconds than the star will emit in its entire lifetime. So we're trying to understand how much more energy gamma rays have. These are quite scary. They can do a lot. We're basically sending energy throughout the universe in a very quick and very small, compact fashion. Right? These are what gamma rays can do. All right. We don't use them on humans. We don't really use them for much. What we mostly do is we try to shield ourselves from them. This is why you don't go really near radioactive material, because radioactive material gives off a small amount of gamma rays, right? So we try and stay away from them. All right. So after doing this, you can do read question 6 and 7 anticipation guide, and then read the section. All right. Oh, there's no vocab. Isn't that nice? Okay. There's a lab on page 651. You don't have to email me or anything like that. Okay. What I do want you to do is I do want you to just try it if you like. If you got a few minutes, you're just hanging around, try this lab out and see what I mean. You can actually measure what frequency your microwave is at. I believe this is the microwave lab, okay? It's pretty cool. So give that a shot, all right? I know I talked a lot. Key things from this is basically how EMR was discovered, how EMR is both electric and magnetic radiation, and how EMR is, how do we say this? The different sizes of EMR, different ideas of what they do, and then memorizing its 400 nanometers to 700 nanometers. All right, have a good one.